Welcome to the Deep Dive. Today, we want you to treat this like a professional slide deck briefing, detailing how raw rock is mathematically engineered for our global infrastructure.
Yeah, because the next time you walk on a sidewalk or drive down the highway, you aren't just standing on a pile of crushed rocks. You're actually standing on a really strict mathematical equation.
Exactly. So on this first slide, we examine the granular skeleton. Think of it like packing a moving van, right? You need large furniture in small boxes to perfectly fill that 70% volume without wasting any space.
Right, and those furniture requirements change completely depending on what you're building. I mean, concrete, asphalt, and railway ballast, they all have completely unique void requirements.
Wait, so they don't just use the same rocks for everything?
Oh, definitely not. Concrete needs high packing efficiency, to get the optimal bond surface area. But asphalt, well, that's graded for stability and exact binder film thickness.
The railway ballast.
Ballast needs interlocking strength plus really rapid water drainage. The costs of failure, if you treat them all the same, are severe.
Right, like needing excess cement to compensate for poor concrete packing, which I'm guessing destroys budgets.
Exactly. And in asphalt, poor gradation leads to bleeding or massive rutting. The road literally smears out of the way under traffic.
Oh, wow.
Yeah, and for rail ballast, poor gradation causes track fouling.
Track fouling. What is that?
It's when the voids between the rocks clog up with dirt and debris, leading to structural instability under passing trains.
That is terrifying.
Okay.
So moving to the next slide, let's look at the data. But wait, I have to push back on the physical test mechanics here.
Sure, go ahead.
We measure all this by mass fraction, not particle counts. Why not just, count the stones?
Well, because a single 40-millimeter stone weighs thousands of times more than a single grain of fine sand.
Oh, right.
Yeah, so if you counted by individual particles, the data would be incredibly skewed by billions of tiny sand grains, completely masking the structural load-bearing rocks. Mass correctly reflects the skeleton's geometry.
Makes sense.
And then this data is plotted on a logarithmic scale to create what we call the envelope.
The envelope. That's the shaded tolerance band on the engineer's graph.
Right, exactly. And the rule here is brutal. If the particle size curve exits that shaded engineer's tolerance band on even one single sieve, it is technically out of spec. Total failure.
Wow. Zero margin for error. On this slide, we compare raw materials. Because, a quarry source is dictated by blast energy, right?
Right, the drill and blast energy and the mountain's fracture pattern, whereas a river source is geologically sorted by water flow over thousands of years.
So how does that map to these strict global specs?
Well, in the Americas, ASTM C dominates. They use numbered sizes, like number 57 for concrete. But in the EU, the standard is EN 112620.
And that's metric, right? Using the little big D notations?
Yes, like 4/16. Plus, they have tolerance categories like GC 9015, and neither standard is universally stricter. They just demand entirely different plant controls.
Which brings us to the machinery. Moving to the next slide, let's talk plant engineering. If nature dictates the river deposit or the quarry blast, how do we force the rock to pass these strict envelopes?
That comes down to mechanical levers. A critical one is closing the circuit.
Closing the circuit, meaning what exactly?
Meaning, if your upper limits are exceeded, you configure the plant to send oversized rock back to the crushers. That closed loop locks down your upper sieve limits.
But what if you have too many microscopic fines spiking above the 75 micron threshold? Like, you can't uncrush a rock.
No, you sure can't. That's when you have to integrate washing systems.
Oh, literal washing.
Yeah, exactly. You use equipment to cure the out-of-spec gradations by physically washing those microscopic fines away.
On this final slide, we see the final equation. The contract standard plus the physical source plus the plant configuration guarantees the structural integrity of your built environment.
It really does. But, it leaves us with a real engineering challenge for the future. River plant operators inherently have the least control over feed gradation.
Because nature already did the sorting, and they rely heavily on that washing.
Right. So as natural river sand becomes increasingly depleted and heavily regulated worldwide, what happens to our global aggregate standards?
Wow.
Yeah, how do we maintain that perfect mathematical envelope when those easiest geological sources simply dry up?
That is an excellent, slightly terrifying question for you to mull over. Until next time, remember that the world beneath your feet is mathematically packed. Thanks for taking the deep dive with us.